Hello and welcome to Zoology 142. This is part 1 of our lecture on nutrition, metabolism, and thermoregulation. So the first part of our lecture is going to be on nutrition, and a nutrient is any substance in food that is used for growth, maintenance, or repair. And there are several major nutrients such as carbohydrates, lipids, and proteins, and these form the bulk of the ingested food. They help us provide energy in the form of calories, and they also provide us with raw materials. There are other nutrients as well that are required in smaller amounts, and these are things such as vitamins and minerals. We don't get any calories from these, but they are necessary for our own growth, development, and homeostasis. So even water is technically a nutrient. So in the last slide we said that the major macromolecules were carbohydrates, proteins, and fats. And these are the macromolecules from which we get the raw materials we need to provide energy for our body and also to help repair and maintain our body. And we can get these three macromolecules in the form of fruits, vegetables, grains, proteins, and also dairy. And they make up the food pyramid. You're probably quite familiar with the food pyramid. You've probably been seeing it since you were very young. And basically the way it works is that things that are at the top of the pyramid, like sweets and saturated fats, are supposed to be eaten sparingly, whereas things towards the bottom of the pyramid, such as fruits, vegetables, and also grains, should be eaten in larger amounts. So here's a slightly more detailed example of the food pyramid. Again, we have things that should be eaten sparingly at the top and things that we should get a lot of down towards the bottom. So saturated fats such as butter, also sweets, should be eating sparingly, whereas our whole grain foods, that is complex carbohydrates that have a lot of soluble and insoluble fiber, should be eaten in greater amounts. And so the food pyramid has been developed and constantly revised by the USDA. If you don't know what USDA stands for, you probably should look it up. One thing that there might be a little bit of, the USDA also has a website called myplate.gov. Using this website, you can go on, enter the foods that you eat on a daily basis and compare them to the USDA recommended daily allowance for carbohydrates, fats, etc. There's also a companion website called SuperTracker, and SuperTracker allows you not only to just enter your food, but also to enter the different types of exercise and physical activity you engage in on a daily basis. And once you enter this information, it can generate a report that tells you whether you're getting too much or too little of certain nutrients, and it can also tell you whether your exercise is adequate enough for your calorie intake. So if you're interested in an extra credit opportunity, here's one for you. I will give you 5 points extra credit on your next exam if you generate a SuperTracker report of both your exercise and your food intake for one day. And so this isn't going to be very hard, but it will be a neat experience so you can see just how many calories you're taking in and how many calories are going out. In order to get credit for this activity, you have to upload it to the Dropbox on La Lima by the close of time for the nutrition quiz. Now in this lecture we're going to learn about a lot of different types of nutrients, and it will first seem a little bit daunting that how do we get all this proper nutrition in the diet? Well, as it turns out, the liver is pretty good at interconverting one nutrient into another nutrient, and so a lot of these nutrients can be converted into other nutrients. For example, carbohydrates, if taken in excess, can be converted into fats. There are, however, something called essential nutrients, and these are nutrients that cannot be synthesized by the body and so therefore must be consumed in the diet. And we'll talk more about essential nutrients as the lecture progresses. So let's take a look at the major macromolecules that help us to get energy and also provide raw materials for our homeostasis and growth. The first of these are the carbohydrates, and carbohydrates are things such as starches, breads, cereal grains, and the sources for these carbohydrates is primarily going to be from plant material. We have two different groups of carbohydrates, starches or complex carbohydrates, and these are basically polymers of monosaccharides that are joined together by chemical bonds. There's also sugars, and sugars are smaller molecules, either mono or disaccharides, that are found in ripe fruits, sugar cane, sugar beets, honey, and also milk. Now, one of the things we're going to learn about is that the majority of your calories should probably come from carbohydrates, and that's because carbohydrates are a wonderful source of energy, and unrefined carbohydrates are also an excellent source of insoluble and soluble fiber. This is non-digestible plant material that helps with the movement of food throughout the digestive tract, and it can also help to lower your cholesterol levels, and we'll talk about that in a little bit. Okay, so what are the uses for carbohydrates in the body? Well, the major use of carbohydrate is to generate energy. Glucose is one of those monosaccharides that can be used to generate ATP. And if you remember, ATP is basically the energy transfer molecule that we use to power various cellular processes. And so if you're getting an excess of glucose or other sugars in the diet, we can convert those into a polysaccharide, for example, glycogen, that will be stored in both the muscles and the liver, or we can even convert it into some fat. And we'll talk more about these interconversions as the lecture goes along. So now we'll take a look at the dietary requirements for carbohydrates in the diet. Basically, according to the USDA, your average American should get at least 100 grams per day in their diet to maintain adequate blood glucose levels. It's recommended, in fact, you get around 130 grams of carbohydrate a day, and that 45 to 65% of your calorie intake should be from carbohydrates. And that's because carbohydrates, again, are an excellent energy source, and they don't have any of the health concerns associated with them like saturated fats do. The other thing that non-refined carbohydrates have going for them is that many of them are associated with fibers. That is, they have either soluble or insoluble fiber attached to the plant material, and that helps with digestion, helps to move food through the digestive tract, and it also helps to lower cholesterol. And so the best choices for carbohydrates is to look at your whole grains and also your vegetables. Okay, now let's take a look at lipids. Lipids are basically fats, and there are two different types of fats in the diet. The main one that gives us energy are the triglycerides or neutral fats. That is, it's a glycerol molecule attached to 3 fatty acids. And we can have saturated fats or unsaturated fats. Saturated fats are things like we find in cheese and butter and other animal fats, whereas unsaturated fats tend to be liquid at room temperature, and we're talking about things like olive oil and canola oil. And so in general, you want to get more of your calories from unsaturated fats than you do saturated fats, because saturated fats are associated with a greater risk of, that's right, heart disease. Okay, there's another lipid we need to talk about called cholesterol, and cholesterol is not really a lipid that we get a lot of energy from, but it is a lipid that's necessary to maintain our cell membranes, and it's also used to make hormones. And so we get cholesterol in our diet principally through things like eggs, shrimp, some meats as well, and if we get too much cholesterol in the diet, that can also put us at risk for heart disease. An interesting thing to know about cholesterol is we actually generate the majority of cholesterol that circulates in our bloodstream in the liver. So even if you're eating a low cholesterol diet, you could still have high cholesterol. While we're on the subject of lipids, we should talk about the essential fatty acids. These are fatty acids that cannot be generated by the body, so they must be consumed in the diet. And these include linoleic acid and linoleic acid. And so if you want to find out where linoleic and linoleic acid come from, stop the lecture right now, get up on the internet, and do a Google search, because this question might just show up on the next exam. So there's several different uses for lipids in the body. They do help to absorb fat-soluble vitamins such as vitamins A, D, E, and K. And they're also a major fuel source for our hepatocytes and skeletal muscle. These are organs of the body that run very well on fatty acids. In addition, phospholipids are essential in the formation of the myelin sheaths of neurons and also all cell membranes. As you probably already know, excess lipid tends to be stored in adipose tissue, which not only offers a storage for excess calories, but it also helps to protect and insulate organs of the body. Finally, prostaglandins are a type of lipid that can stimulate smooth muscle contraction, which can help regulate blood pressure and also inflammation. And finally, don't forget that cholesterol is an essential component of cell membranes, just like our phospholipids, and it's also a precursor of bile formation and steroid hormones. So according to the American Heart Association, we're supposed to get less than 30% of our total number of calories from fat. And that's because eating high-fat diets puts us at greater risk for cardiovascular disease. And so our goal is to eat less than 30% of our calories from fat, when in truth most Americans are getting over 40% of our calories from fat. So we're actually at a greater risk of cardiovascular disease than we need to be. Okay, on to our next macromolecule, which are the proteins. Remember, proteins are made up of amino acids. And so the dietary sources for proteins are things like eggs, milk, fish, most animal meats, as well as soybeans. And we call these complete proteins because they contain all of the essential amino acids needed by the body in order to synthesize its own proteins. On the other hand, foods like legumes, nuts, and cereal grains are called incomplete proteins. That's because they're missing one or more essential amino acids. So in order for the body to use these incomplete proteins to make its own proteins, we have to supplement with other foods that contain the missing amino acids. So for example, we can eat both legumes and cereal grains together, both of which are incomplete proteins, in order to manufacture complete proteins in the body. So there's a lot of different uses for proteins in the body. Protein is used to make up structural materials in the body. For example, keratin found in the skin, as well as collagen and elastin. These make up the bulk of connective tissues and also muscle proteins. Proteins can also be functional molecules, for example, enzymes. Remember that enzymes are microscopic little proteins that help to catalyze or speed up certain chemical reaction. And finally, we should also point out that amino acids can also be broken down for energy. You've heard about people that are on these low-carb Atkins diets where they're basically getting no carbohydrate in their diet, and yet their body's able to keep itself going because we can oxidize and metabolize those amino acids into ATP. So they can be a useful energy source. This brings us to the all or none rule. Remember that complete proteins were proteins that had all of the essential amino acids. By eating a complete protein, we can break that down and then reassemble it within our body to make our own cellular proteins. Now, on the other hand, if you eat an incomplete protein, you don't have all the amino acids you need to make the proteins in your body. And so if you don't have them, we tend to just break that protein down and metabolize it for ATP production, and we don't tend to use any of it for production of our own proteins. So again, it's imperative that we get all of the essential amino acids in our diet in order for our cells to continually repair and replace their own proteins. So according to the USDA, the average American should be getting around 0.8 grams of protein per kilogram of body weight. And this comes to about 55 grams of protein for a person that weighs 150 pounds. Well, as it turns out, most Americans are getting far more than they need to in dietary proteins. And this can be a bad thing because diets that have excessive amounts of protein can actually put us at greater risk for example, osteoporosis, and they can also put us at greater risk for certain types of cancers. So in general, Americans need to cut back a little bit on the protein. So we've just finished up a discussion about the three macromolecules, which are fats, carbohydrates, and also proteins, which form the bulk of the diet and are also the source for ATP production. Now we're going to talk about some of the things that are not used for energy production, but are necessary for body maintenance and homeostasis. And these include both vitamins and minerals. Vitamins are organic compounds that are crucial to helping the body use various nutrients. Many of them, in fact, act as coenzymes. Remember, an enzyme is a molecule that helps to speed up or catalyze a chemical reaction. Now, some of these vitamins can actually be synthesized by our intestinal bacteria and absorbed in the large intestine, but the rest must be ingested in the diet. Now, it's important to realize that no one food contains all the vitamins and minerals that you need, so this is why it's important to get a well-balanced diet that draws from a variety of food groups. So vitamins are divided into 1 to 2 groups based on their solubility in water. Water-soluble vitamins include things like vitamin C and also vitamin B12. Now, these vitamins cannot be stored in the body, so any excess that you get in the body will just be excreted in the urine. And this is why it's pretty useless to take megadoses of vitamins, for example, that you see on the supplement information here. You can see that the supplement contains over 1,667% of the USDA recommended allowance for vitamin C. But it's really not going to do you any extra good because that excess is just going to be lost in the urine. So do yourself a favor and save your money and don't buy the megadoses of water-soluble vitamins. On the other hand, vitamins A, D, E, and K are fat-soluble vitamins. That is, they're best absorbed when eating a fatty meal. Unlike water-soluble vitamins, fat-soluble vitamins can be stored in the body, and so it's important not to get too much because excess amounts of fat-soluble vitamins can actually be toxic. Minerals, on the other hand, are inorganic molecules that are needed in the diet. And there are 7 minerals that are required in moderate amounts, and these include things like calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. You probably already know that calcium is necessary for strong bones, as is phosphorus. Potassium is needed for muscle contraction, and sulfur is needed for synthesis of nucleic acids. And sodium and chlorine are both important electrolytes, which are used to maintain the osmolality of body fluids and also help with nerve impulse conduction. In addition to these major minerals, the body also needs small amounts of certain trace minerals, for example, iodine and iron. Iron, as you know, is used to help synthesize hemoglobin, which is an essential oxygen-carrying molecule, whereas iodine is a necessary component of the thyroid hormone thyroxine. Now that we've learned about the different types of macromolecules that the body uses for nutrients, we're going to shift topics and talk more about metabolism. In order to understand metabolism, it's important to understand what energy is. Energy is basically the capability to do work. And there are 2 different types of energy in the body: kinetic energy, which is energy in motion, and potential energy, which is energy that is stored. So a good example of kinetic energy in the body is the energy of molecular motion. As molecules move throughout a fluid, they bounce off one another, and the faster they move, the more energy in the solution. So one way to increase the amount of molecular motion is to increase the heat or temperature of a solution, thus increasing the amount of kinetic energy. Another type of energy in the body is potential energy. Potential energy is basically stored energy. And a good example of potential energy is this boulder that's resting at the top of the hill. We know that the boulder is not doing anything right now, but all it takes is a little bitty push to get that boulder from a basically static, stationary state to a state where it's rolling very quickly down the hill. And so all we need is a little bit of activation energy to get this potential energy converted into kinetic energy, the energy of motion. Another example of potential energy is the energy that's stored in food molecules and also in fuels. And it's important because the chemical bonds in these molecules contain lots of energy. And all we need to do is break these bonds, and then we'll release that energy, and we can use it to either power our car, as in the case of gasoline, or we can use it to fuel our bodies. So there are 3 macromolecules in our diet that contain significant amounts of potential energy. And these include carbohydrates, proteins, and lipids. We measure the energy content of these molecules in something called a calorie or kilocalorie. A calorie is a unit of energy, and specifically it's the amount of energy needed to raise the temperature of 1 milliliter of water 1 degree Celsius. Most of the times when we're talking about foods, we actually measure things in kilocalories, that is 1,000 calories. And so we say that carbohydrates have 4 kilocalories per gram. That is, 1 gram of carbohydrate will contain 4 kilocalories of energy. Proteins also contain 4 kilocalories of energy per gram, whereas lipids contain 9 kilocalories of energy per gram. So they're much more efficient at storing energy in a small space. So now that you know the caloric value of both carbohydrates, proteins, and fats, you should be able to look at the nutrition information for any food item and tell me how many calories are in there. So let's take a look at something called the KFC Double Down Burger. The Double Down Burger was basically KFC's answer to the Atkins diet. People that were on Atkins weren't eating a whole lot of cheeseburgers because the cheeseburger had a lot of carbohydrate in the bun. And so one way to avoid this amount of carbohydrate was to get rid of the bun. Just take the burger and slap it in between 2 pieces of, that's right, fried chicken. And so the KFC Double Down Burger was a burger with bacon in between 2 pieces of fried chicken. And so here you can see the nutrition information for that burger. It contains 32 grams of fat, 11 grams of carbohydrate, and 53 grams of protein. Given this information, how many calories are in a KFC Double Down Burger? Well, first let's take a look at the fat. There are 32 grams of fat in the burger, and remember that fat stores a total of 9 kilocalories per gram. So simply we take 32 and multiply it by 9, and we see that 288 calories come from fat. Now let's go take a look at carbohydrate. We can see that there are 11 grams of carbohydrate in the Double Down Burger. How many calories are in a gram of carbohydrate? Remember, the answer is 4. So we simply take 11 grams and multiply it by 4, and we get 44. So the 11 grams of carbohydrate contribute a total of 44 calories. Now let's take a look at the protein. Our nutrition information indicates there are 53 grams of protein in the Double Down Burger. How many calories are in a gram of protein? It's just like carbohydrate. There's 4. So we take 53 multiplied by 4, and we get 212. That is, 212 calories come from protein. In order to find out the total number of calories, all we need to do is add up the calories from fat, the calories from carbohydrate, and the calories from protein. If you do this, you'll see that there's a total of 544 calories in the KFC Double Down Burger. So just looking at the calories, it doesn't actually seem that the Double Down Burger is that unhealthy. That is, there's not like 1,000 calories in it, only about 544 calories. And you probably know that the average person should be consuming somewhere around 2,000 to 2,200 calories per day, and so you could eat 3.5 to maybe 4 of these a day and still stay within your caloric balances. But now let's compare it to the RDA recommendations by calculating the percentage of calories that are contributed by fat. In order to calculate the percentage of calories from fat, you simply take the calories from fat and divide them by the total number of calories in the food item. For example, in this situation, we simply take 288, which is the number of calories from fat, and divide it by 544, which is the total number of calories in the Double Down Burger. And so by calculating this, we can see that the Double Down Burger gets a whopping 53% of its calories from fat. Remember that the USDA recommended that fewer than 30% of our total calories should come from fat, and that's because diets that are high in saturated fat are going to put us at greater risk for heart disease, obesity, and other diseases. And so this doesn't mean that you shouldn't eat Double Down burgers, but maybe if you do eat them, that you eat them in moderation. That if you eat a Double Down burger one day, maybe you should eat a salad the next day. And that's because we want to minimize the number of calories that come from fat, particularly saturated fat, because it puts us at greater risk of heart disease. Okay, now we're going to shift gears and focus on cellular metabolism. Metabolism is the sum total of the chemical processes that occur in living organisms which result in growth, production of energy, and elimination of waste and reproduction. And there are two different types of metabolism: anabolism and catabolism. And it's important to realize that enzymes play key roles in both anabolic and catabolic processes. So from Zoology 141, you should remember that ATP, or adenosine triphosphate, is the main energy transfer molecule in the body. That is, it's a high energy molecule that can be used to fuel various cellular processes. And the potential energy here is stored between the second and third phosphate bonds in the adenosine triphosphate. Now we can use an enzyme to break down ATP into ADP. That is, we take adenosine triphosphate and we remove the terminal phosphate bond to make something called adenosine diphosphate. In doing so, we release energy, and so we call this a catabolic process. A catabolic process is a process which tends to break down larger molecules into smaller molecules, and which oftentimes will release energy, and so that's why we call it catabolic. We can also do the reverse process. That is, we can take ADP, which is the discharged form of ATP, we can take an extra phosphate and glue it back on using some energy to make a high energy molecule called ATP. And so this is an anabolic process. An anabolic process is a process where we take smaller molecules and we combine them together, we put some energy into it to make a larger molecule. And that larger molecule usually has more potential energy than the smaller molecules we made it from. And so we say this is an anabolic process. Remember, anabolism means to build, and for example, people that take anabolic steroids are looking to build lots of muscle mass. And so that can help you to remember the difference between anabolic and catabolic. In addition to understanding the difference between anabolism and catabolism, we must also understand what oxidation and reduction mean. Oxidation is a process where we remove electrons from one molecule, and this results in a decrease in the potential energy of that molecule. That is, it's a catabolic process that releases energy. It's important to note that most biological oxidations also involve the loss of hydrogen, so we say that they are dehydrogenation reactions. On the other hand, reduction is an anabolic process. It results in the addition of electrons, or hydrogens, to a molecule, and it results in an increase in the energy content of that molecule. So it is an anabolic reaction. Remember, oxidation, catabolic; reduction, anabolic. So one way to memorize the definition of oxidation reduction is to remember the mnemonic device oil rig. This will help us remember that oxidation is loss of electrons, whereas reduction is gain, oil rig. Now up to this point we've been talking about oxidation and reduction as if they were opposite reactions that can happen independently. But this is really not true. Chances are if we're having oxidation occur, we're also having something else being reduced. And so we say that oxidation-reduction reactions are coupled. That is, one's happening and then the other one's happening. So let's take a look at an example. So on your left-hand side, you see an example of succinic acid. You don't need to know what succinic acid is, but you do need to know that we're going to break this molecule down into fumaric acid. Now, how does succinic acid differ from fumaric acid? Well, take a look at the red H's. We have 2 hydrogens for each of the middle carbons on succinic acid, and only 1 hydrogen for each of the middle carbons on fumaric acid. So those hydrogens were lost. And remember, loss of electrons or loss of hydrogens is oxidation. And so succinic acid becomes oxidized into fumaric acid. So where did the hydrogens go? We can see FAD has taken them. FAD grabs a hold of the hydrogens and takes them away. So FAD has become reduced. That is, it has grabbed a hold of electrons, whereas succinic acid has become oxidized. So you might be wondering from the previous slide just who the heck FAD was. Well, FAD is an electron carrier molecule just the same as NAD is, and so they exist in both oxidized and reduced forms. For example, on the top you can see that NAD plus is the oxidized form of the molecule. When it grabs a hold of two hydrogens from another molecule, it becomes NAD reduced. And that NAD reduced also releases a hydrogen ion. Now let's take a look at FAD. FAD is the oxidized form. If it grabs a hold of two hydrogens, it becomes the reduced form. And so NAD and FAD are important electron carrier molecules that help to transmit the potential energy that is released when food is broken down, and eventually they're going to help us to convert that energy into ATP. Okay, so one more example of an oxidation reduction reaction. Let's take glucose, C6H12O6, and combine it with oxygen and see what happens. Well, the cells will convert that carbon that is in glucose into carbon dioxide. And you can see that carbon dioxide is a smaller molecule than the glucose is. And so we say that glucose is oxidized into carbon dioxide, whereas oxygen is reduced into water. That is, initially we just had oxygen gas, but if we look at the oxygen on the other side of the equation, we see that it in fact is joined with hydrogen to make 6 water molecules. So glucose becomes oxidized into carbon dioxide, and oxygen becomes reduced into water. And in the process, we release some energy in the form of ATP. So now that we've learned about oxidation and reduction reactions, let's return to our focus on cellular respiration. The whole point of cellular respiration is to release the potential energy that is locked in the food molecules that we've eaten and use that energy to make ATP. So depending on how you split it, cellular respiration is a 3 or a 4-step process. And these steps include glycolysis, an intermediate step, the Krebs cycle, and the electron transport chain. So for each of these 4 steps, you should be able to answer the following 4 questions. Where does each of these steps occur? What are the starting and ending products? Does this process require oxygen? And how much energy, that is ATP, do we get out of each step? So this diagram just shows an overview of where the 3 processes occur. Glycolysis happens out in the cytosol, that is the cellular jelly that surrounds the organelles, whereas the Krebs cycle and electron transport chain both happen within the mitochondria. Now your book goes into quite a bit of detail about the process of cellular metabolism, and this detail can be a little bit hairy if you haven't had chemistry in a long time, so I'm going to dumb it down just a little bit. We're going to start with the first step, which is glycolysis. And look at what that word means. Glyco meaning sugar and lysis meaning to split. And so we're going to split a sugar into a smaller molecule. The sugar we're talking about here is glucose, which is a 6-carbon molecule. So I'll just draw it out here as a linear 6-carbon chain. In truth, it's more of a pentagon or a hexagon, but it'll be easier to follow what's going on with the molecule if we just look at the carbons and if we look at them in a linear format. So glucose is a 6-carbon molecule. Now the first step of glycolysis is the splitting of this 6-carbon glucose molecule into 2 3-carbon PGAL molecules. And in order to do this, we actually end up spending 2 ATP to get the process going. And this is called the energy of activation. Now in the next step of glycolysis, we're going to convert those PGAL molecules into something called pyruvate. In the process, we're going to release some high energy electrons, and that energy is going to be used to phosphorylate ADP and change it into ATP. And so in this process, we generate a total of 4 ATP. So 4 ATP, that sounds pretty good, but let's remember that we actually had to spend 2 ATP to get the whole process going. So our net production of ATP is actually 4 minus 2. So in essence, we only get 2 ATP out of the process of glycolysis. And while we're on the subject, I should note that another name for glycolysis is substrate level phosphorylation. And substrate level phosphorylation is just a fancy term that indicates we're able to generate some ATP without the presence of oxygen. Oh, that's right. Remember that glycolysis does not require oxygen, and so it can happen in anaerobic environments. So remember the ending product to glycolysis was something called pyruvate, which was a 3-carbon molecule. Now, what happens to this pyruvate will depend on whether or not we have oxygen present. If there is oxygen present, we can simply place that pyruvate into the Krebs cycle and oxidize it to extract the rest of the potential energy. On the other hand, if there's no oxygen present in the body, we're going to have to metabolize this pyruvate through the process of fermentation. For example, in the human body, pyruvate can be converted into lactic acid. And this happens in particular when we don't have a lot of oxygen in our muscle cells. And lactic acid is responsible for that burn that you feel after you've exerted yourself or done a lot of anaerobic exercise. For example, if you're lifting weights and you can feel that muscle burn is caused by the incomplete breakdown of glucose into lactic acid. And it's the lactic acid that is responsible for the burn. Probably another example of fermentation that you're familiar with is the fermentation of alcohol. That is, we can take pyruvate and convert it into ethyl alcohol, which is a 2-carbon compound. And so the ending products for glycolysis and fermentation are either going to be a 3 or a 2-carbon compound. So the question is, do any of these compounds still have potential energy left? So the correct answer to this question is yes, absolutely, these molecules still have a lot of potential energy. Glycolysis has released only a fraction of the chemical energy present in glucose. We still have much more chemical energy that can be released when these molecules are broken down with the help of oxygen. For example, think about the potential energy that's in ethyl alcohol. Ethyl alcohol is in beer, it's in wine, and you probably know that if you drink excessive amounts of ethyl alcohol, not only will you get drunk, but over time you'll actually start to put on weight. So our body is able to convert the potential energy in pyruvate and in ethyl alcohol into ATP, and this excess energy can be stored as body fat. So now let's assume that we do have oxygen to help continue the breakdown of pyruvate. Remember, pyruvate was a 3-carbon molecule, and then we had 2 pyruvate molecules exiting glycolysis ready to enter the Krebs cycle. Before we go through the Krebs cycle, we'll need to go through an intermediate step. In the first part of the intermediate step, each of the 3-carbon pyruvate molecules will enter the mitochondria. 1 carbon of each of the 2 3-carbon fragments will then be removed as carbon dioxide gas. The remaining 2-carbon fragment is an acetyl group, and this will combine with a coenzyme A to form something called acetyl coenzyme A. And acetyl coenzyme A will then enter the Krebs cycle. It's important to realize that this step actually happens twice. That is, it happens once for each of the 2 pyruvate molecules which exited glycolysis and entered the intermediate step. Now let's take a look at the Krebs cycle. The starting substrate for the Krebs cycle is a 2-carbon fragment called acetyl coenzyme A. This acetyl coenzyme A will be fed into the Krebs cycle. Now, if you take a look at your textbook, you'll see that there are a lot of complicated steps that happen within the Krebs cycle, but the gist of this is that both carbons of the 2-carbon acetyl coenzyme A molecule will be oxidized to form carbon dioxide gas. In the process of this oxidation, we will create 2 ATP molecules, that is, 1 ATP for each of the acetyl coenzyme A fragments. Our electron carrier molecules, NAD and FAD, will grab a hold of the high-energy electrons and hydrogens resulting from this oxidation. So in essence, NAD and FAD will become reduced. And it's important to realize that NAD and FAD here are carrying the majority of the potential energy that was initially in glucose. That is, these high-energy electrons and hydrogens are going to be transmitted to the electron transport chain, where we're eventually going to extract the potential energy and use that to synthesize much more ATP than we've gotten thus far. We should also remember that the Krebs cycle, as well as the intermediate step, both require the presence of oxygen. So now let's talk about the electron transport chain. The electron transport chain is a very complicated process that happens within the membrane of the mitochondria. Basically, NAD and FAD drop off their high-energy electrons, and they are transferred down something called cytochromes. And as these electrons travel down the cytochromes, they release some energy. This energy is absorbed by the mitochondrial membrane. Just like the Krebs cycle, the electron transport chain needs the presence of oxygen, because oxygen is a very electronegative molecule that is helping to pull the electrons down the cytochromes. The potential energy absorbed by the mitochondrial membrane will then be used to pump hydrogen ions from the inner mitochondrial compartment into the outer mitochondrial compartment. We then have special proteins which will allow the diffusion of the hydrogen ions back into the inner mitochondrial compartment. And in the process, we will use this downhill flow to synthesize ATP from ADP. The hydrogen ions will then combine with oxygen to make what we call metabolic water. The big picture here is that in the process of the electron transport chain, we generate a total of 32 to 34 ATP. So the majority of ATP coming from the catabolism of glucose actually occurs during the electron transport chain. And this slide just gives an overall summary of the events happening during glycolysis, the Krebs cycle, and the electron transport chain. Remember, at the beginning of glycolysis, glucose entered the cytoplasm, and glucose is a 6-carbon molecule. In the process of glycolysis, it was broken down into 2 3-carbon fragments called pyruvate. In the process of this, we got 2 ATP without the benefit of oxygen. In the intermediate step, we had our pyruvate being broken down into acetyl coenzyme A, which would then enter the Krebs cycle. The remaining carbons are lost in the Krebs cycle as carbon dioxide gas, and in the process, we generate another 2 ATP. Remember that the Krebs cycle happens within the mitochondria, and it requires oxygen. And the final step of cellular respiration was the electron transport chain. And remember, the electron transport chain also required oxygen. And here we had the high-energy molecules NAD and FAD dropping off high-energy electrons at the mitochondria. And these electrons were used to energize the cytochromes, which then used that energy to pump hydrogen ions from the inner mitochondrial compartment to the outer mitochondrial compartment. And the downhill flow of hydrogen back through that inner mitochondrial membrane was used to phosphorylate an additional 32 to 34 ATP, and we call this oxidative phosphorylation. So in grand total, we've gotten somewhere between 36 and 38 ATP throughout the process of cellular respiration. The majority of these ATP were realized in the process of the electron transport chain. Now, in the example that we gave, we concentrated mainly on the catabolism of glucose in order to provide ATP. But it's important to realize that we can also use fats and amino acids to generate ATP as well. The big difference is that neither fats nor proteins will go through glycolysis. We'll simply convert these molecules into pyruvate and feed them into the mitochondria, where they will go through the Krebs cycle and the electron transport chain. So the big picture here is that we can extract energy from both fats, carbohydrates, and also proteins. In order to extract energy from fats and proteins, we specifically need the presence of oxygen because these only utilize the mitochondria, that is, the electron transport chain and the Krebs cycle, whereas we can get a little bit of energy out of glucose through the process of glycolysis, which does not require oxygen. But either way, if we have oxygen present, we're going to get a lot more ATP out of the food molecules that we eat. So you should know by now that there are 3 macromolecules that the body can use to extract energy. These include carbohydrates, fats, and amino acids. In general, the body will try to burn carbohydrates first, and then fats, and if we have none of these left over, we'll start to burn amino acids or proteins. And we can convert each of these molecules into other molecules. For example, we can convert a carbohydrate into a fat if there's excess carbohydrate in the body. And the amount and direction of this conversion is directed by both the liver, the adipose tissue, and also skeletal muscle. So a couple of the important metabolic processes accomplished by the liver are glycogenesis and glycogenolysis. Remember that glycogen was a polysaccharide storage form of sugar. Basically, we linked several sugars together to form glycogen. And so this is the process of glycogenesis, the manufacture of glycogen. Basically, glucose molecules are linked together by chemical bonds to form the polysaccharide glycogen, resulting in glycogenesis. The opposite process is called glycogenolysis. This is the splitting of glycogen into individual simple sugar molecules. And glycogenolysis happens when we're not getting a lot of carbohydrate in the diet, and so the liver will break down that glycogen to release glucose for the bloodstream. Because remember, although several of the organs can run on fatty acids, the brain and nervous tissue must run on glucose. And that's an important reason why the liver must go through the process of glycogenolysis, splitting of glycogen into glucose. But you might ask what the body does when we run out of glycogen. Well, this does happen in certain circumstances when somebody's been exerting themselves and they depleted all their glycogen stores within their muscle and also within their liver. In this case, we're going to manufacture glucose through the process of gluconeogenesis. Let's take a look at this word and see what it means. Gluco means sugar, neo means new, and genesis means to form. So we're forming new glucose from a previously non-carbohydrate source. So through the process of gluconeogenesis, we can convert both proteins and also fats into glucose, which is needed by the brain and nervous tissue. And it's important to realize that gluconeogenesis is stimulated by cortisol and glucagon. These were two molecules which help to elevate blood sugar in cases where blood sugar starts to drop below set point levels. So now that we've talked about the interconversion of carbohydrate, let's take a look at lipids. What are lipids used for in the body? Well, some lipids, of course, are going to be broken down to make ATP. And remember that lipid is a very rich source of potential energy because each gram of fat contains 9 kilocalories of energy. So there's a lot of potential ATP there. If we have excess calories consumed, some of that lipid, in fact, is going to be stored as adipose tissue or body fat. In other cases, lipids can be used as structural molecules or to synthesize essential molecules. Examples include phospholipids, which are used to construct plasma membranes of cells, lipoproteins that are used to transport cholesterol, and thromboplastin, which is important for blood clotting. Another important function of lipids is they are used to synthesize the myelin sheath of neurons. Remember, neurons transmit information via nervous impulses, and by having this myelin sheath, we can greatly accelerate the speed of nerve transmission. And finally, we should also remember that cholesterol is a lipid that can be used to synthesize bile salts and also our steroid hormones such as estrogen and testosterone. Now, just like with glycogen, we can also catabolize lipids to produce energy, and this process is called lipolysis or lipolysis. This is the process of splitting triglycerides into individual fatty acids and a free monoglyceride, and this can be used to generate ATP. If we're breaking down a lot of fat molecules through the process of lipolysis, we can actually generate some molecules like beta-hydroxybutyric acid and acetone. These substances are collectively known as ketone bodies, and their formation is called ketogenesis. And it's important because the heart muscle and also the cortex of the kidney prefer to use these molecules for ATP production. However, if we have excessive amounts of ketones generated, we can have a process called ketosis occurring. Ketosis indicates that the body is primarily using fats for fuel. Either we're eating only fats or we're breaking down our own body fat reserves because we're starving. And the excessive lipolysis and ketosis can actually lead to a condition called ketoacidosis, which leads to an abnormally low blood pH. People that are in ketoacidosis will often have a sweet acetone-like smell to their breath, and we typically see this in patients that are diabetic and haven't been treated well with insulin. And so without insulin, they cannot break down sugar, and so they're relying on the fat stores in the body and generating lots of ketone bodies. Another instance where we can see ketosis is in people that are in high-fat diets or people that are on diets that include no carbohydrate. This is often called the ketone diet, and people will monitor their urine for the presence of ketone bodies, which is called ketonuria. And the presence of ketones in the urine indicates that the body is in fact burning fat. And if you're not getting enough calories in the diet, this is a sign that your body is metabolizing its own body fat and that you can expect to see a drop in your body fat percentage. And although it's a very popular diet, it's not one that I would recommend because ketoacidosis can be a life-threatening condition. So in the previous slides we talked about the breakdown of fat, that is lipolysis and ketogenesis, but now let's talk about lipogenesis, which is the creation of fat. So we can take any molecule, for example proteins and carbohydrates, if it's consumed in excess and we need to store that energy, we can convert those molecules into lipids and store those within our adipose tissue. And the process of lipogenesis is stimulated by the hormone insulin. Okay, now we're going to shift gears and move away from triglycerides and talk more about cholesterol. Remember, cholesterol was another lipid in the body that we don't really use for energy production, but it is an essential nutrient used to synthesize different structures in the body. For example, cholesterol is the structural basis for bile salts, which are used to emulsify fats in the GI tract. It's also used to synthesize steroid hormones, for example estrogen and testosterone, and also for vitamin D absorption. Cholesterol is also a major component of the plasma membranes. Now, you're probably already familiar with the fact that high cholesterol levels can lead to increased risk of cardiovascular disease, but what you may not know is that in truth, only 15% of the cholesterol circulating in our bloodstream comes from the food that we eat. Your liver actually manufactures somewhere between 75 and 85% of the cholesterol circulating in your body. And a lot of this cholesterol can be lost from the body when it's catabolized or secreted in bile salts. And one way to help ensure that this excess cholesterol is lost from the body is to eat diets that are rich in insoluble and soluble fibers. This fibrous material is indigestible and it binds to the cholesterol and prevents its reabsorption in the small and large intestines. Okay, something else we need to talk about is the transport of lipids like cholesterol and triglyceride throughout the bloodstream. Remember that lipids and water usually don't mix, and so we have to have special lipoproteins that make them temporarily soluble in the blood plasma in order to transport them throughout the body and the blood. So there are three major classes of lipoproteins. These include VLDLs, LDLs, and HDLs. The acronym VLDL stands for Very Low Density Lipoproteins, and these help to transport triglyceride from the liver to the peripheral tissues. For example, if you get excess fatty acids in the diet, the VLDLs will transport this material to the adipose tissue in the body where it can be stored. On the other hand, LDLs primarily transport cholesterol from the liver to the peripheral tissues, and here it can be clogged in blood vessels and lead to arterial sclerosis and also cardiovascular disease. And finally, HDLs, or high-density lipoproteins, do the reverse process of LDLs. That is, they help to transport excess cholesterol from the peripheral tissues to the liver where it will be broken down and secreted into the bile. We oftentimes call this the good cholesterol. Another function of HDLs is that they also help to provide cholesterol to steroid-producing organs. For example, they transport cholesterol to the ovaries and testes, which will secrete estrogen and testosterone. Okay, this slide just shows the composition of the four major groups of lipoproteins that are important in the body. The first of these were our chylomicrons. We talked about these in the previous chapter on the digestive system. Chylomicrons were important for transporting triglyceride from the intestines to the liver, and so they're going to be made primarily of triglyceride. That is, 80 to 95% of their composition will be triglyceride. On the other hand, the VLDL and LDL are synthesized by the liver. The VLDLs are composed of about 50 to 65% triglyceride and 10 to 15% cholesterol. Remember, the VLDLs were used to transport excess fatty acids from the liver to the adipose tissue of the body. On the other hand, the function of the LDLs was to transport cholesterol from the liver to the peripheral tissues of the body. So the major component of LDLs is going to be cholesterol. And finally, our HDLs, they were used to return excess cholesterol to the liver where it's broken down and excreted from the body. And so they contain only about 20% cholesterol, and the majority of the molecule is made up of phospholipids and also proteins. So now let's talk about recommended levels for cholesterol in the body. Most of you know that cholesterol is associated with a greater risk of cardiovascular disease, and so we want to keep our total cholesterol number at or below 200 milligrams per deciliter. If it gets above that, we're going to put ourselves at greater risk for arterial sclerosis and other types of cardiovascular disease. You should remember from the previous slide that the HDLs were often called the good cholesterol because their function was to transport excess cholesterol from the peripheral tissues back to the liver where it's broken down and secreted from the body. And so ideally we want our HDL lipoproteins to be as high as possible. So ideally they should be above 60. Below 40 is not good. And finally, our LDLs, or low-density lipoproteins, are what we commonly call the bad cholesterol. That is, high LDL numbers typically result in a rise in our risk of cardiovascular disease. So ideally, we want our LDL levels to be at or below 100 milligrams per deciliter. If they're above 130, we're going to be at a greater risk for cardiovascular disease. Now, most of us know that eating a diet low in saturated fat and cholesterol is one way to ensure that we don't have high cholesterol levels in the blood. But there are also some non-dietary factors that can affect our cholesterol level. One of these is stress and cigarette smoking. Both of these tend to reduce the amount of HDL in the body and therefore create a greater impact of the LDL cholesterol. A factor that can increase your cardiovascular health is aerobic exercise. Aerobic exercise and also estrogen both help to elevate the HDL levels, which results in a decrease in LDL levels. And this is why exercise is so beneficial to cardiovascular health. And finally, body shape can have an effect on your LDL levels. If you store all your fat up in your abdomen, we say that you have an apple shape, and this can result in increased LDL levels, whereas if you have the fat stored primarily in your hips and buttocks, we say that you have a pear shape. And although we'd argue that it's not good to be overweight at all, if you had to choose, you'd rather be a pear, because people with pear-shaped bodies tend to have lower cholesterol and LDL levels. Now, even if you exercise and even if you eat a low cholesterol diet, it's possible that you can still have high levels of cholesterol circulating in your bloodstream. And that's because the liver actually synthesizes about 85% of the cholesterol in the body. And so some people will just have a genetic propensity to high cholesterol levels. In this case, the only thing we can do is prescribe medication which can help to lower that cholesterol. And the major medication being used today to lower cholesterol are the statin drugs, for example, Lipitor. And it's currently estimated that around 10 million Americans take statins like Lipitor, and they can be very effective at reducing the blood cholesterol levels, but some of them also do have some pretty gnarly side effects. So now we're going to shift gears one more time and talk about protein metabolism. Proteins tend to deteriorate quickly in the body, so they must be continuously broken down and replaced by new proteins. We can recycle some of our amino acids and reassemble them into new proteins in the body. It is important to realize that protein cannot really be stored in the body. So when dietary protein is consumed in excess one day, we tend to oxidize those amino acids for energy and store any excess as fat. But this means that eating a lot of protein, let's say on Tuesday, will not guarantee adequate amounts of amino acids on Thursday. If you're not getting adequate amounts of amino acids on Thursday, you can actually go into a protein deficit. And so that's why it's important to get the adequate amount of protein in your diet each day, which is around 0.8 grams per kilogram of body weight. So we already said that one of the things we can do with excess protein is just break it down and metabolize the amino acids to produce ATP. And this is a very complicated process. We're not going to go into any detail, but one of the things I want you to realize is that this metabolism happens in the liver. And so we have to have a liver that is operating correctly, and we should also note that the catabolism of amino acids also generates some pretty toxic byproducts. And one of these is called urea. Urea is a nitrogen-containing compound which results in the deamination or removal of the amino group from amino acids. And if this builds up in the body, it can become toxic very, very quickly. So it's essential that we have a liver that's functioning correctly and also kidneys that are functioning correctly to get this urea out of the body. If, for example, the kidneys are not operating at 100%, we can actually get an increase in the amount of urea and nitrogen-containing compounds within the bloodstream, and this is called azotemia. Now, we already said a few slides back that proteins were things that needed to be repaired and replaced all the time because they're very, very delicate. And so we have to have enough amino acids in our diet in order to be able to repair and replace the proteins in our body. And this repair and replacement is controlled by hormones and requires that we have all the essential amino acids from our diet. If we're not getting them in our diet, we can actually end up with protein deficiency, and we won't be able to repair or replace the proteins that are damaged in our body. And in your lifetime, it's interesting to note that you're going to synthesize somewhere between 225 and 450 kilograms of protein. Now remember that 1 kilogram is equivalent to 2.2 pounds, so it's possible that in your lifetime you're going to synthesize over 1,000 pounds of protein. So now that we've completed our overview of the different types of interconversions that can happen with proteins, carbohydrates, and fats, we're going to look at the metabolic adaptations that allow our body to maintain adequate levels of glucose in the bloodstream when we're eating and when we're fasting. We call these states the absorptive and post-absorptive states. The absorptive state happens when we're ingesting food, and that food is being broken down in the small intestine and absorbed through the GI tract. In this case, glucose is going to be readily available for ATP production. And remember, the organs that require glucose are things like the brain and spinal cord. They run exclusively on glucose. Now, on average, it's going to take us about 4 hours to digest a meal. And so, if we're eating 3 meals a day, we're going to be spending about 12 hours of the day in the absorptive state. And in both the absorptive and post-absorptive state, the metabolism is going to be regulated by hormones such as insulin, glucagon, epinephrine, and also cortisol. So now let's take a closer look at the regulation of metabolism during the absorptive state. Remember that in the absorptive state, your small intestine is absorbing the nutrients from the food that you've just eaten and digested. And in this case, the rising blood glucose levels and increased levels of GIP, or gastric inhibitory peptide, are going to be the cues for release of insulin by the pancreas. And insulin is the primary hormone released during the absorptive state. And insulin has several functions. First of all, it's going to increase several anabolic reactions. For example, it's going to help us to synthesize storage molecules such as triglyceride from the other types of macromolecules in our diet. For example, if we got a lot of glucose in a meal and we don't need it all to fuel our cellular processes, we're going to go ahead and convert that into triglyceride or fat so it can be more easily stored. On the other hand, it's going to decrease most of the catabolic reactions in the body, so it's going to slow those down. Insulin also helps to promote the entry of glucose and amino acids into cells so they can use that for their own metabolism and cellular repair, and it also stimulates the phosphorylation of glucose so we can extract ATP from it. And finally, insulin also stimulates protein synthesis along with the synthesis of thyroid and growth hormone. So this picture just gives an overview of the major metabolic processes that are happening during the absorptive state. Remember that during the absorptive state, we're absorbing nutrients from the food that we've just digested, and one of these nutrients is glucose. And some of that glucose is going to be used to generate ATP through both oxidative and non-oxidative phosphorylation. Any excess glucose can be converted into triglyceride, which will be a storage form of energy that can be called upon for later use. We will also use that glucose to synthesize glycogen. Remember, glycogen is a polysaccharide created by linking several glucose molecules together by chemical bonds. Other processes happening during the absorptive state include the uptake of amino acids into the cells and also the production of glycogen in the muscles. So the big picture here is that during the absorptive state, we're primarily doing anabolic processes. That is, we're using glucose to make glycogen, we're converting glucose into body fat, and we're also helping to move the amino acids into the cells so we can synthesize proteins. There are a few catabolic reactions going on. For example, we might use some of that glucose to make ATP. So while the absorptive state happened while we were actively absorbing and digesting food, the post-absorptive state happens about 4 hours after a meal. This is the case where we have already distributed all the energy molecules throughout the body, and now we have to call upon those reserves to continue to fuel the body and produce adequate glucose levels for the brain and spinal cord. So the hormones that are important here are going to be glucagon, epinephrine, and also cortisol. And these are hormones that help to elevate blood glucose. And they do this by stimulating glycogenolysis, that is the breakdown of glycogen into glucose, and in some cases stimulating gluconeogenesis, that is the formation of glucose from non-carbohydrate sources. Now it's important to point out that the hypothalamus is actually the command center from moving us from an absorptive state to a post-absorptive state. So the hypothalamus will detect low levels of blood sugar, and sympathetic neurons from the hypothalamus will release norepinephrine to the adrenal medulla. And this will cause an even greater release of norepinephrine and epinephrine, which will stimulate the breakdown of glycogen and also stimulate the breakdown of fat or lipolysis. These two catabolic processes will help to raise blood glucose levels to make sure that we have adequate levels of glucose for both the brain and spinal cord. Okay, so this picture just gives an overview of the major metabolic processes going on during the post-absorptive state. Remember, in the post-absorptive state, we have no food in the intestines, no nutrients to be absorbed. All the nutrients that we had absorbed have been stored in our adipose tissue, in our liver, and also in our muscle tissue. So in this case, we have to start to call upon those reserves and liberate those macromolecules so that we can provide enough glucose for the brain and spinal cord, which don't run very well on any other type of molecule. So one of the factors that we will favor is lipolysis. That is the breakdown of fat into fatty acids, and those fatty acids can be used to produce ATP and also be converted into glucose. Another process that is favored by the post-absorptive state is glycogenolysis. This is the breakdown of glycogen, a polysaccharide, into glucose. And this glucose, again, is fed into the bloodstream so that it can supply the brain and spinal cord. So remember that the major hormone that's active here is going to be glucagon, which helps to elevate blood glucose, and other hormones that are important during this phase are epinephrine, norepinephrine, and also cortisol. So the big picture here is that the post-absorptive state involves primarily catabolic processes, where we're breaking down our storage forms of energy in order to maintain adequate blood glucose levels for the brain. Okay, we're going to shift gears once again and focus on energy balance. Energy balance is basically the difference between the energy coming in and the energy going out. And the energy intake, again, is from the food that we eat, and the energy in that food is liberated in the process of digestion and absorption. And the energy output is going to be through various forms. It's important to realize that even though the human body is very efficient at utilizing energy, over 60% of the energy we absorb is going to be lost in the form of heat, and this is a non-usable form of energy. The other energy is going to be used to generate ATP, which will be used to do work throughout the body. For example, it will keep the brain alive and the kidneys alive and so forth. And finally, any excess energy that we get in our body that is not used for generation of ATP or heat will be stored as either fat or glycogen. Now, for most Americans, we tend to get more energy input than we do energy output, and this can result in obesity or a greater than normal body weight as a result of accumulation of body fat. And so one way to determine if somebody is obese is to calculate a body mass index. To do this, you simply take their weight in pounds and multiply that by 705 divided by their height in inches, and this will give you a number. And if that number is less than 25, it indicates that you're an ideal weight, whereas if it's between 25 and 30, it indicates that you're overweight. Numbers that are over 30 indicate that that person may in fact be obese. And recognizing obesity is important because obese people tend to have a higher incidence of cardiovascular disease, type 2 diabetes, hypertension, and osteoarthritis. And you're probably aware that obesity is actually an epidemic in America because we have more adults and children overweight now than we did 20 years ago. And even though Hawaii is deemed one of the most healthy states, it's because we have a large proportion of people out there that are exercising profusely, while there's also an equally large proportion of people that aren't exercising at all. So the rate of obesity may be overall very low in Hawaii, but when we tend to look at certain ethnic groups or social groups, we see that obesity is still a very large health risk for people here in Hawaii. If you don't want to use the equation on the previous page to calculate your body mass index, you can use this graph here. And on the left-hand side of the graph, you can see your height in feet and inches, and on the top part of the graph, you can see your weight in pounds. So let's look at an example. Let's look at somebody that is 5 feet 10 inches tall and is 195 pounds. So we go 5'9" and go over to 195, we'll just call it 200, and we can see that they are actually in the obese zone. And so that would indicate that they have a BMI of 30 or greater. And remember, somebody that has a BMI of 30 or greater is going to be at increased risk for cardiovascular disease, diabetes mellitus, and several other different types of disorders. Now, I know this lecture is already getting long enough as it is, so we're not going to talk about the factors that regulate food intake, but I would like you to read about these in your textbook because we will have 1 or 2 questions on the exam about the endocrine and also nervous signals that lead to an increase or decrease in food intake. So now we're going to talk about some of the treatments for obesity. Obviously, if you have somebody that's just slightly overweight, one of the things you can consider is dieting, simply restricting the amount of food and the number of calories coming in so that we're exhausting or expending more energy than we're bringing in, and that should result in weight loss. But probably most of you have gone on a diet at one time or another and know that it can be very hard to stick to that diet, particularly if you're talking about losing 30 or 40 pounds. In a case of somebody that is morbidly obese, let's say that's 50 or 100 pounds overweight, we might want to consider something slightly more drastic. And that includes surgical procedures, for example, the gastric bypass surgery. In the gastric bypass surgery, we basically disconnect the stomach from the esophagus and also from the duodenum, the first loop of the small intestine. And we reroute the jejunum, the second loop of the small intestine, up to a pouch that's created just off the side of the esophagus. And so this helps to facilitate a rapid weight loss in 2 ways. One, it really reduces the amount of food that can be consumed and stored in this sort of new stomach. Initially, these people can only eat a few tablespoons of food at a time. The other thing it does is reduce the amount of absorptive area of the digestive tract. So in essence, people can be eating a normal amount of calories, but only a small proportion of these calories are absorbed by the new GI tract. And gastric bypass surgery, although it's severe, can have very good outcomes. It can help people to rapidly reduce their body weight, and conditions that were developed while obese, for example, type 2 diabetes, oftentimes will resolve themselves and go away completely. And of course, no discussion of the metabolism or food intake would be complete without talking about the metabolic rate. The metabolic rate is the rate at which we burn calories and produce heat, and it can be measured directly using something called a calorimeter, or it can be measured indirectly using something called a respirometer. So both of these are trying to get indicators of how quickly we are burning calories, because even though the average person should consume somewhere between 2,000 and 2,200 calories a day, your individual metabolic rate will depend on the amount of physical activity that you do, and also on whether you're male or female, and also on your levels of thyroxine. Thyroxine is the primary hormone which helps to set your basal metabolic rate. So your basal metabolic rate reflects the energy the body needs to perform its most basic and essential functions. So this is things like the energy needed to circulate blood throughout your blood vessels, the energy needed to ventilate your lungs. It does not include exercise or any kind of extraneous activities. It's simply the basal amount of energy you need to stay alive. And so we measure the BMR, or basal metabolic rate, of somebody while they're in the post-absorptive state. That is, they can have nothing to eat for 12 hours, and we'd put them in a reclining position and make sure that they're relaxed both mentally and physically. And we maintain the room temperature in an ideal setting of around 20 to 25 degrees C. And this ensures that they don't have to expend any energy for sweating or energy for shivering if the environment is too cold. And so we record the basal metabolic rate in kilocalories per square meter of body surface area per an hour. And so the basal metabolic rate is influenced by the body surface area, the age, the gender, and also the body temperature, any types of stress, and also the thyroxine production. For example, people that produce high levels of thyroxine tend to have higher basal metabolic rates, whereas people that produce low levels of thyroxine have lower basal metabolic rates. So here are some factors that influence the basal metabolic rate. In general, BMR tends to increase as the ratio of body surface area to volume increases. Basically what this means is that smaller people tend to have proportionally higher metabolic rates than larger people. The basal metabolic rate also decreases with age. That is, as you get older, you need fewer calories to maintain your BMR. Males tend to have a disproportionately higher BMR than females. That's because in part they have more muscle tissue, and this muscle tissue requires more calories just to keep it going. BMR also increases with temperature or stress. For example, if you're in a very warm environment or a very stressful environment, you will tend to burn more calories than if you were in a more comfortable or relaxed environment. And remember, thyroxine is the primary hormone that's helping to set our basal metabolic rate. So if you have more thyroxine, you're going to have a higher BMR. Finally, it's important to point out that physical training really has little effect on BMR. You can be a very athletic person, but your calorie consumption to maintain your tissues is not going to be much different than somebody of the same size and gender who doesn't have a lot of physical training.